Hello guys, my name is Ganesh Shankar Bhandari and I am here to take the live session for week 8 for the course NPTEL course Principles of Casting Technology taught by Professor P.K. Jha, IIT Roorkee. We will wait for 10 minutes. We will see if anyone join. Hello, Satrudan. We will start in 5 minutes. We will wait if anyone other joins, then we will start. Okay.
Okay, sir, I'm waiting here.
Okay. Okay, so we will start with our today's lecture. So today we will talk about the casting defects and how to uh, analyze them. Where are the defects in casting? Until yet, we have learned about how to create a casting and what types of different casting processes are there, and after you have reached with your final casting, so you have to check the casting for the defects inside them, because if there is any defect inside your casting, so you will not be able to use them in your desired applications, because due to those defects, the life cycle of that casting can be decreased, or that can create severe problems. Okay, so I am taking the help from the slides which you have been provided in your NPTEL lectures. So first we will talk about defect in casting. So what are the casting defect, their types, and their cause, and what can be the remedies to avoid them. Okay. So coming to the casting defects, there are mainly five types of casting defects. First is gaseous defects. Okay, So these types of effects are created due to the when you are going to pour your castings inside your molds. Okay, so there will be some moisture inside, there can be some moisture inside your cast molds. Okay, if you are going with the sand molding process, so definitely there is going to be some moisture inside casting. So that moisture due to high temperatures is going to convert into vaporized form. Okay, so that will uh, come out from your castings. Okay. Second thing is that if there is any volatile matter present in your molten metal, so that is also going to react with your sand or other things, and it is going to get out from that mold. Okay. So due to those gaseous retrievation of from the castings, there are going to be some gaseous defects created in your casting. So first is blowholes, then open blows, air inclusion, and pinhole porosity. So blowholes are created due to when your casting is going to expand. Okay, you have put your molten metal inside the mold, and your casting is going to expand due to gaseous entrapments. Okay, so that will create the blowhole inside the casting. Okay, then open blows, other comes air inclusion. So if any air is trapped inside your casting, okay, so that will create the air inclusion effect in your castings. So for remedying these types of defects, what we generally do before pouring the molten metal inside your sand castings, okay, we generally burn that casting. Okay, we provide some maybe we can provide some kerosene or something like that. So we are going to burn it. Okay, so during burning, what will happen, because the burning requires oxygen. Okay, so during that burning process inside the casting, whatever the oxygen is present inside the mold, okay, that is going to consumed out. Okay, so if oxygen is not there, okay, your air is going to consume down due to that burning inside the mold. Okay, so there will be no air present inside your mold now. Okay, then you can pour your molten metal inside the casting, so any air inclusion or any blowhole type of gas defects will not be going to come there. Okay, so you will create a sound casting. Then coming to shrinkage cavities, that we have already discussed about in previous lectures, what are the shrinkage cavities and how to uh, avoid them. Okay, for avoiding shrinkage cavities, what we do, we generally use risers. Okay, so by the use of riser, we can avoid the shrinkage cavities, because riser is going to cool down at last, and it is going to continuously provide the molten metal inside the during the casting solidification process. Okay, so there will be no shrinkage cavity will be coming inside your final casting. Then coming to third defect, that is caused by molding material defects. Okay, so molding material defects can be cuts and washes, metal penetration, fusion, run out, rat tails, and buckles, swell, drop. So coming to cuts and washes, this type of molding defect generally comes during when you are trying to uh, put your molten metal into the permanent castings. Okay, so in case of permanenting, most of the time in case of permanent casting, there are two halves of casting. Okay, if the design is a little bit intricate, so you are going to create two halves of that permanent mold. Okay, and you are going to punch them together with the help of nut and bolts. Okay, so you are going to create a cavity. Okay, so if there is any porosity remains inside that during that uh, joining of those two halves, okay, so what will happen, or if the nut and bolt system is not properly clamped, okay, so what will happen? Your molten metal will apply the pressure on that permanent mold, and from those joints, okay, that is going to come out, because metal has some certain specific pressure. So that is going to come out from those joint. Okay. So that will create cuts and washes. And when we talk about metal penetration, we generally talk about sand casting processes. Okay, so if sand is not properly rammed, okay, so your metal will apply the pressure on the sand walls, okay, sand casting sand mold balls, and it is going to penetrate inside that mold walls. Okay, because the sand has not been properly rammed for making mold. Okay, so that will not sustain with the pressure exerted by the molten metal. So your sand is going to erode inside the molten metal, and that metal penetration defect will come inside your castings. Then coming to fusion, so fusion defect generally created when we are trying to put the molten metal inside the inside the mold via two or more gates. Okay, so what will happen, because metal is coming from one gate and then second gate. So if proper fusion is not there, okay, for two molten metal streams, whatever is coming from different sides, so your fusion defect will come into the picture. Then run out defect generally created due to the low fluidity of molten metal. Okay, you have some intricate design. Okay, and your fluidity of the molten metal is not proper to get inside in that cavity. Okay, so that will create the run out defect. Then coming to rat tail, that will also created due to improper ramming of your sand during molding process, and buckle swell drop will also create due to that improper ramming of sand mold. Then coming to the other defect, pouring metal defects. Okay, so pouring metal defects are created due to the during the pouring of your molten metal inside the castings. So first defect is misruns. Okay, so misrun is basically a defect which is created above the casting, wherever you have provided the gating system or pouring system, wherever you have provided, so there will be created that misrun defect. Okay, so what will happen, you are going to pour your molten metal inside the gating system or pouring system, and by mistake you have the molten metal has poured out from that pouring basin. Okay, so that is going to solidify on that on that location only, and that will create your misrun defect. Okay, so in the final casting, that uh, solidified metal onto that surface is going to come with your casting. Okay, and to remove that defect, you have to provide some fettling or something like that. You have to cut it out, you have to grind it out from that your design, final design, so you can get your desired casting. Okay, and cold suds is also coming due to your fluidity. Okay, if molten metal fluidity is not as much as required, so what will happen, from two gates if metal is coming, okay, so that is not going to properly fused out. Okay, due to that low fluidity of metal, it is going to solidify earlier, and it will create your cold sud. Then slag inclusion. Slag inclusion comes from your during your smelting process. Okay, or it can come from your sand also. If slag is going to inside your if sand is eroded and going inside into your molten metal, so it will create the slag inclusion. And for the remedy of this slag inclusion, we provide bob. Okay, or we provide filter inside your sprue. Okay, so that slag is going to filter out during into your sprue only. Okay, so that slag is not going to include into your final casting, because what will happen if slag comes inside your casting, that will create the brittleness inside your casting, because slags are generally having ceramic type properties, and ceramics, we know, they are very brittle in nature. So your final casting will not be going to have the strength what you wanted. Okay, then coming to another defect, those are metallurgical defects. uh, First is hot tear, then hot spots. Those defects generally comes from either with your alloying materials. Okay, hot tier defect generally comes with through the sulfur. Okay, if sulfur content is very high, if you talk about mild steel casting, and if sulfur content is very high inside your mild steel casting, okay, so what will happen? That sulfur is going to react with your molten metal iron, and it will create Fe sulfide. Okay, iron sulfide, and that iron sulfide has a lower melting point compared to your mild steel. For example, mild steel has a melting point of around 1450 or 1500 degrees Celsius, and iron sulfide has a melting point of only 800 to 900 degrees Celsius. And what will happen, that Fe sulfide is going to uh, create at the grain boundaries. Okay, I think somebody wants to join. Okay, so what will happen, that Fe sulfide is going to precipitate at your grain boundaries. Okay, and during the when we talk about heat treatment processes, during that heat treatment process, that Fe sulfide is going to melt before the because general when we talk about heat treatment process, we talk about temperature of around 950 or 960 degrees Celsius, and that Fe sulfide is going to melt at only 800 degrees Celsius. Okay, so what will happen? Your grain boundaries are going to melt down, and when you are applying pressure on during your heat treatment process, if you talk about forging process or something like that, then that your whole casting is going to tear apart from those grain boundaries. Okay, because those have been already melted down, so your whole casting will get broken up, and you will not be able to provide the any heat treatment process or any forging or any hot working processes on your castings. Okay, then coming to hot spots, these are also created due to some metallurgical defects, or we can say due to improper heat transfer from mold to outside. Okay, those hot spots get created. Then coming to some more metallurgical defects, there are micro porosity. These comes from the gas inclusion or something like that. Then sand blow, you can see that sand blow defect is coming due to the uh, blowing of sand. That sand is going to erode it inside your casting, and that will come with your final casting. So as you can see, this is surface of casting, and that is blow. Okay, that has come due to the sand. Okay, that sand has got penetrated inside this molten metal, and due to that penetration of sand, the molten metal has not been able to solidify in this area. Okay, so that will create a blow on your castings, and if you want to remove this defect, then there is no other option than to cut this casting from here. Okay, so that blow is going to get removed from your casting. What will happen, you are going to you lose the dimensions of your castings. Okay, you have to compromise with the dimensions of the casting. Then coming to pinholes defect, these comes due to the improper heat. We can say if gases are not going to uh, if gases are not getting the passes to get out from your sand molds, then these types of defects will create inside your castings. Then coming to shrinkage cavity, as we can see, if we are not going to provide the proper riser system to the castings, so there will be shrinkage cavity formation. Then metal penetration, or you can say misrun. We have talked about misrun. So misrun is basically created due to the lower fluidity of your molten metal. So we want molten metal to flow up to this point, but this has been due to low fluidity of the molten metal, this has been solidified here only. Okay, so this area is not going to filled up by the molten metal, because the gating or whatever the area was there from the cross section from which molten metal is going to pour inside this section, that has been already blocked by the solidification of your cast molten metal. So that will create the misrun, and that will definitely change the final properties of your casting, final dimensions of your casting. So you will not be able to use that casting into desired applications. Then coming to cold stud, then now we have talked about casting defects. So we have talked about casting defect, their causes and remedies. Now we will talk about how to check these casting defects inside your casting, whatever the casting defects are coming inside your casting, because not all, there is not always the things that that will create on the surfaces only. Okay, the casting defects can be inside your mold, inside your castings also. So you have to check those. If we talk about surface defects, then you can see with your naked, sometimes you can see them with your naked eyes also. So you are going to fatal it out or something like that. However, however the final casting dimensions are going to be changed, but you can provide some treatments for removing those defects. But if the defects are inside the castings, so how you are going to check them? Because the inside defects, you have not seen them, and those inside defects are going to create the problems during life cycle of that casting. Wherever you have employed that casting, that is going to create the problems. So coming to the defect diagnostics in castings process, we talk about non-destructive testing methods. Okay, why we use non-destructive testing methods? Because we don't know if if the castings, whatever we have created, it is a sound casting or it has some defects inside those castings. So we go with the non-destructive testing methods because we don't want the destruction of casting or any addition of the defects inside the castings. Okay, uh, during your testing methods, because if you are going to take a sample out from that casting or like that, something like that, so what will happen if the casting is not going to have any defect? Okay, if the casting is not having any defects, so due to that, whatever the sample you have taken out, that has destroyed your castings. Okay, so you will not be able to use that castings finally. Okay, so we go with the non-destructive type testing methods. So we are not going to change any physical or any metallurgical properties of castings during these testing methods. That's why they called as non-destructive testing methods. So coming to the types of non-destructive testing techniques, there are similar many types of NDT testing methods which carried out to check the soundness of casting and control of microstructure in some cases, etc. Then coming to testing techniques, there are some testing techniques which based on visual inspection, magnetic inspection, penetrant, radiography, fluoroscopy, ultrasonic, eddy current, and pressure testing. So now we will discuss about every no, NDT testing methods one by one. So coming to the visual casting, non-destructive testing technique, it's just like you are going, uh, you are trying to see the defects inside your casting which are on surface, which can be seen by the naked eyes. Like if we talk about blowholes, okay, so that can be seen by visual inspection only. Okay, you can check them that blowhole has been created on your casting surface, or misrun defect has come. So you can some defects are there which you can just analyze with the help of visual inspection of the casting. So you can provide some remedies to create a sound casting after those visual inspection by fettling or by grinding or by welding techniques. So you can provide the remedies. Okay, then coming to the magnetic inspection testing. So in magnetic particle testing, these types of tests on generally applied on the ferromagnetic materials only. Okay, because you need some magnetic properties inside your material, then you can only apply the magnetic particle testing procedure on your castings. And these types of NDT testings are uh, uh, generally employed for checking the pores, or we can say the defects on the surface which are which you are not able to see with your naked eyes. Okay, so what we will do, we will apply a magnetic field or flux in a ferromagnetic material, and due to that surface tension, we will put some powder, okay, magnetic powder on the surface of your casting, and we will provide magnetic field. So what will happen, wherever wherever there is a crack inside on the surface, okay, so what will happen, your magnetic particles or whatever powder you have, magnetic powder you have provided on the surface, that will go inside that surface cavity. Okay, so due to the flow of that magnetic powder inside, as you can see, there is a magnetic field, there are magnetic field lines, and we have put some magnetic particles in green color on the surface of your casting. So what will happen, when you provided some magnetic field into this sample, so what will happen, this powder will move towards this crack. Okay, so due to that movement of powder, you can analyze the surface defects on your castings. But the limitations of this type of testing is that you will be only able to test ferromagnetic type material with this type of NDT testing. Okay, you can't test your aluminum alloy or copper alloy with the help of magnetic particle testing. You can only go with this type of testing for iron alloy, or you can say nickel alloy or nickel super alloys. You can go for this type of testing. Then coming to the second one, penetrant test. So in this penetrant test, this is generally a alternative for your magnetic particle testing, because we had already talked about magnetic particle testing can only be applied on the ferromagnetic materials. So for non-ferromagnetic material or dimagnetic material, what we can do, we can go with some penetrant test. So what we will do, we will put some dye, okay, or we can say some color, something, some dye solution. We will pour that dye solution onto the surface of the casting. Okay, so what will happen, wherever there is a crack, okay, so what will happen, that dye will penetrate inside into that crack. After the penetration of that dye solution inside the crack, what we will do, we will apply some fluorescent light or UV light. Okay, we will inspect that casting in the presence of UV light. Okay, so whatever the dye we have provided on the surface of that castings, that is going to illuminate in the presence of in the presence of UV light. Okay, so you will be able to inspect the defects on the surface of the casting. Okay, so these types of penetrant test can be applied on the dimagnetic materials also. So the applications of magnetic particle testing and penetrant test is around similar, but the difference is only that in case of magnetic particle testing, you will be only able to apply it on ferromagnetic material, while penetrant test can be applied on any type of material. Then coming to the next one, radiographic testing or fluoroscopy. So in this radiographic testing, what we have talked about surface defects. So surface defects can be easily inspected with the help of visual inspections only, or we can go with magnetic particle testing or dye penetrant testing. So what will happen if the defects are inside the surfaces? Okay, so we cannot go with magnetic particle testing or your dye penetrant testing, because that will not penetrate inside the surface, because there is no hole or porosity. So those magnetic particles or liquid dye can get inside into the castings. So checking the inside defects for casting, we generally go with the some different techniques like radiographic testing, or we can go with eddy current testing or ultrasonication testing type process. So penetrating ionizing radiations are passed through components. Okay, so what we are doing, we are passing some radio waves from the surface. Okay, as you can see, we are passing some x-rays uh, from the castings. So these X-rays are going to penetrate inside your casting. Okay, it will not create any defect or something like that into your casting. So these X-rays are going to penetrate inside the casting, and on the other face you are going to take a replica of the uh, because these, when you are putting the X-rays inside the casting, so either they are going to absorb, or they are going to reflect it, or they are going to transmit it down from that sample. Okay, so what you will do, you will create a X-ray of that castings on the second on the lower side. Okay, from upper side you are penetrating this with the help of X-ray or radio waves or other waves, and at the bottom hand you are creating a replica. Okay, so due to that X-ray, it's like same principle as you go to any orthopedic when your bones are fractured, or bones are fractured, so you go to orthopedic, and they do a X-ray testing on your bone, and they create a replica. Okay, so they came to know that where is the crack inside your bone. Okay, so it's just like that. Okay, so radiographic testing or fluoroscopy, we generally go with fluoroscopy. Images produced on the fluorescent skin with the help of X-rays penetration, so you are going to get the defects inside your casting. Then coming to the next one, ultrasonic testing. So in ultrasonic testing, it's like ultrasound. Okay, so frequency of sound that penetrates the section gives an indication on the instrument screen. Layer of grease or a proprietary coupling agent between probe and casting surfaces to allow transmission of sound into casting. So what will happen, you are going to provide some ultrasonic, you are going to penetrate ultrasound into your casting, and that will come back. Okay, so wherever there is a defect inside your casting, the sound velocity will get changed. Okay, so due to that change in velocity of sound or ultrasonic waves, because you are putting the ultrasonic waves with a similar speed inside your casting, but with what speed it will come back, okay, that will depend on your casting defects. Okay, if there is any defects inside your casting, that can come back from that point only. Okay, because sound will not travel in vacuum, and if there is any defects inside your casting, that will create as a that will act as a vacuum. Okay, so your sound is not going to travel into that vacuum, that will come back from that defective surface only. Okay, so according to that time period, you can create some you can with the help of some mathematical calculations, you can create a replica in of defects inside your system. Whatever the defects are there, you can create a replica of them. So okay, so that is ultrasonic testing. Then coming to eddy current testing. In this test, alternating current is passed through a coil, which is when brought closer to part being tested, a disturbance in current flow is created. Okay, so it is also like magnetic particle testing or magnetic field type of testing. So just what we are doing, we are creating a electric field, okay, surrounding to your casting. So if there is any defect inside the casting, so magnetic field pattern will get changed. Okay. Due to that change in pattern, you are going to detect your casting defects inside the castings. So as you can see, if any crack or we can see in this casting, that is a sound casting. So magnetic fields are constant in going into concentric circles only. If there is any crack, okay, inside the casting, so these concentric circles paths are going to get changed. So due to that change in path, you can detect the cracks position inside your castings. Okay, then coming to leak detection testing, there is bubble test and helium mass spectrometer test are there. So what we are going to do, we are going to if we create some hollow casting or something like that. Okay, so what we are going to do, we are putting it into some bubble test or helium mass spectrometry test. We are going to provide insert some gases inside that casting, and we are going to detect the leakage inside those castings. So these are few casting defect non-destructive testing methods which we use for detecting the castings, surface castings or inside defects into your castings. So you can check if whether your final casting can be used inside your desired applications or not. So now we will go with some MCQ type of questions based on these NDT testing methods and your casting defects inside the. So coming to the first question, dash following the blanks, filling the blanks involves the removal of riser and excess material while grinding. So what is the procedure which we use to remove the riser and excess material while grinding? Okay. So any answer? So what we are talking about fettling procedure. Okay. So when we talk about casting procedure, we talk about riser, we talk about gating, we talk about sprue system. There is a whole for creating a sound casting. We provide many additional things, additional systems with your castings. Okay, with your molds. There are riser, there are gating system. So when we are going to fill the molten metal inside your mold, okay, so that riser your gating system is also going to get filled with the molten metals, okay, and with during the solidification process those riser and gating systems are also going to get solidified with your castings, okay. So when that has been solidified you are going to take that casting out the sand mold, okay. So removing those riser and gating systems or excess material whatever we have provided during during the casting process, so what we need to do, that process is known as pickling, that process is known as impregnating, fettling or short peening effect. So coming to the answers, first is pickling. Okay. So pickling is basically pickling is known as the surface removal process. Okay. Surface whatever the dirt or whatever the when you are going to create a casting. Okay. So your surface is uh, not going to be smooth. Okay. So, or we can say there can be oxidation on the surface also. So, removing that oxide layer, we generally go with the pickling process. Okay, for removing that oxide layer from the surface, what we are going to do, we are going to put your whole casting into some mild acid, okay, with some zero point 0.5 or 1 molar molarity of HCl acid generally we use for pickling process. Sometimes we also use H2SO4, okay. So we are going to put that inside that uh, low molarity acid, okay. So what will happen, that oxide layer is going to get removed from the surface, okay. So pickling process is generally not used for removal of riser and excess material, okay. Then impregnating, that is also like pickling. Then coming to fettling, okay, that process is generally known as for the removal of riser and excess material, okay. With the help of grinding, with the help of grinder we are going to cut the excess materials from your casting, okay. Then coming to short peening, this is basically for the this method is generally employed for two different reasons. First is to remove that oxide layer from the surface, okay. Second is with the short peening effect we create cold working on the surface of your casting, okay. In short peening effect, short peening method, what we do, we put our casting inside a chamber and we throw the stainless steel balls with very high speed onto the metal casting. Okay, so what will happen due to that high speed of metal balls, that is going to impact those balls are going to have very high impact force on the surface of your casting, and due to that high impact and abrasion forces, what will happen, the surface layer of your casting is going to get removed, so you will get a new shining surface, and then you can go with the grinding procedure or welding procedure, whatever you want, to create the final casting. Okay, so answer is fettling. I think someone. Okay. Okay, coming to next one. Which of the casting defects can be avoided by increasing permeability of the mold? So we are talking about permeability of the mold. Okay, we are increasing the permeability of mold. So what casting defects can be avoided with the increasing permeability of the mold? Air inclusion, hot tear, swell or rat tail. So any answer?
Red tail.
No. Actually, rat tail effect is generally created due to the improper ramming. Okay, improper ramming of the sand. Okay, because rat tail will create like this. When we talk about rat tail, so that is if that is your mold. Okay, so your metal is going to penetrate inside this mold, this sand. Okay, so final casting will look like this. Okay, that rat tail will get created. Okay, so that is rat tail, so that cannot be avoided with the increase in permeability of the mold. So when we talk about air inclusion, so air inclusion will be due to the if any air has been trapped inside your castings, uh, so that will be the air inclusion. So avoiding that effect, what we generally do, we burn the whole, we can say, we burn the whole mold, okay, before the before the molten metal pouring inside the casting, so air inclusion can be avoided by that effect. Then hot tear, that comes due to the presence of sulfide elements or phosphorus alloying elements, or we can say that comes due to the improper conduction, okay, between the mold and your castings. Okay, so if heat conduction is not proper there, so that will create the hot tear effect. So coming to the swell, okay, that defect can be avoided by increasing permeability of the mold. So swell effect is what, so that is going to create like this. Okay, so your initial casting was like this, you have created the mold like this, but due to the swelling effect, okay, so your casting will solidify, final solidification will be like this, because that has pushed down your sand, okay, to some extent. And why that will happen, this will happen due to the improper ramming of the mold. Okay, so if we are going to increase the permeability of the mold, or we can say if we are going to increase the permeability of your sand, so that effect will not come, because in that case you can do proper ramming of your mold. So the bonding between two particles of that sand will be on very much higher side, so that will not create the swelling effect inside your casting. Okay, because your casting, whatever the pressure has been exerted with this molten metal, that will not be going to affect your sand mold. Okay, so that is basically swell effect. Then coming to the next one. A is enlargement of the mold cavity by metal pressure caused by insufficient mold pressure. So we had already talked about this earlier. Any answer? So we are talking about enlargement of the mold cavity. Okay. By metal pressure caused by insufficient mold pressure. So we have talked about this defect like this. So your metal casting is going to get swell up. So answer is this. Then coming to the fourth one is caused by the expansion of the surface layers of the sand mold. So we are talking about expansion of the surface layer. So any answer? So we are talking about expansion of the sand mold. Okay. So if casting is like this, okay. So expansion will be like this. If your sand mold has expanded, if we talk about like this, that has been expanded. So what will happen? The final casting which we have created will solidify like this. So there will be a hole, okay, or we can say scab on the surface of your final casting. So expansion scab is caused by the expansion of the surface layers of the sand mold. Okay, because sand mold has been expanded, and due to that your molten metal is not going to get solidified in this region because sand is already taken that place. Okay. When we talk about Mishran, so Mishran is like this. This is your gate. This is your casting. It has to be go until this point, but this has been solidified at this point only. So this defect is known as Mishran. Then we coming about cold sud. So when we talk about cold sud, it is like this. So your molten metal is coming from both directions, and if the molten metal is coming from two different directions, okay, so there has to be proper fusion at the meeting points, okay. But if the fluidity of the molten metal is very low point, or we can say we have not provided the proper superheat to the molten metal before pouring, so what will happen, that molten metal is going to get solidify before getting to the fusion point. So your casting defect will create is at this point. So this is known as cold shut. Okay. Then then we had already talked about the hot tear effect. So these are not the answer. The expansion escape is caused by the expansion of surface layers of the sand mold. Coming to the next one, and fill in the blanks may occur where metal has been agitated or has partially eroded the sand. So we are talking about partially erosion of the sand. So any answer? So we had talked about expansion scab that is created due to the mold expansion. Okay, mold surface layer expansion like this. So that is your expansion scab. Okay, so that cannot be the answer. Then we come into erosion scab. Okay, so it's like vice versa to the expansion scab. In expansion scab, that mold has taken this place. Okay, so your molten metal is not going to get inside on this position. Okay, so your final casting will be hollow from this surface. So some erosion will be created on the surface of that final casting. And in case of erosion scab, what will happen? Your molten metal is going to erode your casting. Okay, so that will be like this. So due to that high molten metal pressure, your sand has been eroded from some point, and due to that erosion of the sand, the cavity has been created and the molten metal has gotten solidify at that point. Okay, so that will create the erosion scab on the sample. So in this case, you are getting casting like this, and in this case you will get some extra molten metal, some extra solidification on your casting. Okay, so that is going to be the answer. And erosion scab may occur where metal has been agitated or has partially eroded the sand. Cold shut we had already talked about, and hot tear we also talked about. So answer is erosion scab. Okay, coming to the next one, the hot tearing in a metal is casting is due to high fluidity, high melt temperature, hindered contraction, or low coefficient of thermal expansion. So why this hot tearing effect is occurring due to? Any answer? Okay. So if we talk about this type of casting, so what will happen? The conduction or solidification, what we talk about metal solidification will be higher on these portions. Okay. But at this point, this junction, okay, your solidification rate is not is your solidification cannot be similar to the rate of solidification at this point. Okay, so here the solidification rate will be different. Okay, so due to this different in solidification rate, what will happen, that metal here is going to get solidify with hindered contraction. Okay, so due to this hindered contraction solidification rate, this hot tearing will happen. Okay, because you are not going to get any, we can say, riser has been already solidified. If riser has been already solidified, or we will not, or if we are not able to provide the molten metal, okay, at that position, because this hot tearing will occur. When we talk about solidification, we talk about three different scenarios. First the liquid is going to get solidified. Okay, so when we talk about solidification, we talk about like this three stages. Okay, so in this region your liquid is going to get solidified. Okay, and then after this region, your here it will be liquid shrinkage, here it will be solidification shrinkage. So during this solidification shrinkage, this hot tearing will come into the picture. Okay, so for liquid shrinkage we can provide the material from the riser. Okay, so that will be avoided. But for solidification shrinkage we cannot provide the material from the riser, because riser also has been already solidified, because that is coming due to the shrinkage in after solidification. So due to that, this solidification shrinkage will create this hot tearing effect due to the hindered contraction, because here the geometry is different, so that will not, we can say, the solidification shrinkage will not occur properly due to the differences in your heat conduction. Okay, so the hindered contraction will occur, or and due to that hindered contraction the hot tearing effect will come into the picture. Because hot tearing is not dependent your high fluidity or high melting temperature or low coefficient of thermal expansion. That is not the cause of hot tearing in the metal. The main cause is hindered contraction. So coming to the next one, misran in a casting arises due to poor fluidity of molten metal, poor green strength, low porosity, or high superheat. So, any answer? This is simple one. You can answer it. We had already talked about misrun. So, what we have talked about, it's like if your casting is like this. So, you have to pour, you want the molten metal to travel up to this point. But if it has gotten solidify on this point only, okay. So, you are not getting any casting here. Okay, you had not get any molten metal here so that it can get solidify and you can get a perfect casting. So what can be the cause for this? So when we talk about the solidification, okay, your molten metal is not getting up to this point, so we talk about fluidity of the molten metal. Okay, so poor fluidity of the molten metal will be the cause for the misrun casting defect, because due to that poor fluidity of molten metal, your molten metal has not get inside into this portion. It has gotten solidify, or we can say uh, we have not provided the proper superheat to the molten metal. Okay, so it has gotten solidify before reaching the end point into the casting. Okay, so poor green strength, that is the characteristic of your sand mold. So that has no uh, hand in the your Michelin casting defect. Low porosity, no, and high superheat. So if we are providing the high superheat to the system, molten metal, then this defect will not occur, because due to that high superheat, the fluidity of the molten metal will get increased, and due to that increased in molten metal fluidity, your molten metal will go up to the last extent of the mold. Okay, so you will not get any misrun casting defect. So the answer is poor fluidity of molten metal will cause the misrun in the casting defect. If fill in the blanks is a defect in which a discontinuity is formed due to the imperfect fusion of two streams of metals in the mold cavity. So we are talking about imperfect fusion of two streams of metal in the mold cavity. So we had already talked about this type of defect. So any answer? So for hint we are talking about this thing. Okay. So molten metal is coming from two different streams, from here and from here, and it has been solidified like this. Okay, so this type of defect is known as your cold shut. Okay, because the imperfect fusion of two streams of metal in the mold has happened due to the earlier solidification of your molten metal. So the cold shut defect will come into the picture, because mission we had already talked about. We had talked about erosion scab, and we had talked about hot tear also. So this type of defect is known as cold shut. Coming to the next one, which of the following statements is are correct? Dye penetrant test is used to detect surface flaws of casting. Then second one, ultrasonic inspection is used to test internal defects of casting. So any answer? Okay, so coming to the question, dye penetrant test is used to detect surface flaws of casting. Yes, we had talked about it. That dye penetrant, because dye cannot be penetrated inside the uh, surface. Okay, it can be penetrate onto the surface defects cavities only. Okay, and ultrasonic inspection is used to test internal defects. Yes, because any other test can for the inspection of ultrasonic internal defects, we can go with ultrasonic inspection, or we can go with eddy current testing, or we can go with radiography also. So these are the different techniques for the inspection of internal test defects. So the answer is both first and second. Then coming to next one, which of the following statement is or are correct? The transducer is used to convert electric energy into sound energy. Magnetic particle inspection test cannot be used for non-magnetic materials. So any answer? Okay. So the transducer is used to convert electric energy into sound energy. Yes, in the ultrasonic testing machine, a transducer is used which convert electric energy into the sound energy. Then coming to the next point, magnetic particle inspection test cannot be used for non-magnetic materials. Yes, it cannot. It cannot be used for non-magnetic materials because we are trying to create a magnetic field on the system, and that can happen with only ferromagnetic materials. So the answer is both first and seconds are correct. Coming to next one, which of the testing method is used to identify the surface defect in casting? Liquid penetration test, ultrasonic testing, Satter test, or annealing? So any answer? Okay, so for surface defect testing, we talked about the liquid penetration test. Okay, or we can go with either go with liquid penetration test, or we can go with magnetic testing also. That will depend on the quality of material. If we are going with ferromagnetic material, then we can go with magnetic testing, or if the material is non-magnetic in nature, then we can go with liquid penetrant test. Then ultrasonic testing is generally used for detection of inside defects. Okay, that cannot be used for surface defect. Then Satter test, it is generally not a NDT type of testing, because in Satter test, this type of testing generally applied in powder metallurgical processes to check the Satter index of the powder balls whichever we have formed. Then annealing, it is basically a heat treatment process, so it is nothing to do with the casting defects or your NDT methods. Then coming to the next one, magnetic particle test is carried out to reveal the location of cracks that extend to surface of iron casting, cracks that extend to surface of aluminum castings, internal voids in iron casting, or internal voids in aluminum casting. So any answer?
Cracks that extended to surface of iron casting.
Yes,
One is the
this is correct because when we talk about magnetic particle testing, we generally talk about ferromagnetic materials and for surface defects. Oh, okay, so cracks that extend to surface of iron castings can be tested with the help of magnetic particle testings. Okay, so answer is cracks. This one. Then coming to next one. Which of the following casting defects occurs due to improper ramming of molding material? Okay,
C.
yeah,
Sorry, D. Both B and C. That means swell and drop.
yes, swell and drop both defects comes due to the improper ramming of molding material. Okay, so that is for today. So any doubt if you want to ask?
Sir, only this question today.
Yeah, if you have any other question, you can ask.
Okay, sir. I want to ask you. Uh, uh, I see the previous question.
Okay.
Yes. Sir, this lecture regarding in NPTEL examination, what will be the maximum question to ask me?
I think I can't say that if these questions are going to come directly into your NPTEL examinations because frankly speaking, I am not aware about the examination procedure. Okay. There are different TAs for that which you might have
No,
meet
no,
in your problem.
not sir, not sir. This lecture, I am saying total lectures.
Hmm. I think there will be questions on the MCQ basis. If you have online examination, so the questions will be MCQ type, or sometimes it can because there are some numericals also. So there can be the questions with the NDT type. You have given the GATE exam or not?
Yes, yes, sir. I want to ask you one question more. Numerical question is also asked in this question in this examination.
Yes, numerical questions will also be there because you had read about gating systems or riser systems. So those portions are purely based on numerical problems. Okay, your Keynes method and whatever we have read safe factor method. So those are purely numerical based problems. Okay,
Yeah.
so
Okay,
that
sir.
can be in NDT type also. Your whatever we like gate exam pattern. So the exam pattern will be like gate only most probably. You will get
Yeah.
some MCQ questions on and some questions you have to provide the values.
Okay, sir.
Anything else you want to ask?
Sir, in types of non-destructive testing,
Hmm.
I mean, Penetration testing.
Yeah, there you can see on your screens there are different types of non-descriptive testing:
Yes, sir.
visual, magnetic, penetrant. These are generally for surface defects
Yes, sir.
only. Okay,
Yes, sir. I want to ask you only penetrant. Uh, so
okay. You want me to explain that penetration
ex-
testing again?
yes, sir.
Okay. So in penetration testing, what we are doing, uh, we are taking a dye, okay, color dye.
Yes,
We are
sir.
mixing it with some water, or we can mix it with some fluids also, other fluid also. So what we are doing, we are putting our sample um, in both way you can do it. Either if your sample size is too small, then you can put your whole sample inside that inside that fluid, okay, which contains color, okay, dye in the form of color. Or if the sample size is bigger, then you can spill it on the surface of that casting, okay. So what will
Yes,
happen
yes, sir.
wherever there is a defects on the surface of casting, okay, so what will happen, that dye is going to penetrate inside that surface, okay. And by naked eyes you will not be most probably by naked eyes most of the time you will not be able to see where that dye has penetrated inside the surface, okay. So what you will do,
Sir,
you huh?
mm, uh, penetrant test is only represent uh, out the surface or inside the surface.
It will penetrate inside the defect which is we can say
We can say
which is coming
inside
on
the
the
crack.
surface actually. The defect has to be has had some connection with the surface. That defect had to be started from surface, okay. Then in that case only that will going to penetrate inside the your defect. It's
Okay,
like
sir.
crack formation of if some crack formation on surface is there, so that crack opening will be on the surface, okay. Sometimes if crack opening is in some micron meter only, so we you will not be able to see that micron meter opening, okay, but the opening is there. So for that case you are going to apply that penetrant test. If the surface opening
Okay,
is
sir.
bigger, it's like if it is in mm, so you will be easily able to see it with your naked eyes also, okay.
Yes, sir.
If the opening is there but you are not able to see it with naked eyes, so then you are going to do check it with the penetrant test, okay. So that liquid is
Okay,
going to
sir.
fill inside that micron meter defect opening, or we can say opening, okay. Then we are going to apply UV rays, okay, UV light on the surface of that sample, okay. So in presence of UV light, that dye penetrant is going to show illuminescence, okay. It's like uh, okay, you had not, you are mechanical background, so had not talked about, you had not read about rare earth materials. Like it's like rare earth materials. When we talk about rare earth materials, they illuminate with different colors inside UV rays. Okay, so you can go with the dye having something like that. Okay, there are some other metals and pigments there that can illuminate when it comes into the contact to UV rays. Okay. So when you are going to put the UV rays or UV light on the surface of that casting, so you will be able to see that color. Okay. So you can mark the area of that defect, and you can go for some remedy. Okay.
Okay, sir. After this penetrate test, what is this another testing?
Um, Once you got to know the casting defects, okay. So you will analyze those defects if they are going to create a bigger problem inside your applications or not. If they are bigger in size, then you cannot use that casting. Okay. If they are
Okay,
in the threshold limit, okay, then you can go with the application process of that casting, or you can analyze if that casting defect. If we talk about surface casting defect, so that will go down into your sample up to some extent. Okay, that level can be micrometer or that can be millimeter. So you can grind that surface. Okay, if that is up to some extent of micron meter only, then you can grind that surface and you can use your castings. And for analyzing the defects inside the castings, okay, it's like if air inclusion is there, we talk about air inclusion inside your casting. So what will happen, that due to that air inclusion, some bubble formation inside your casting will create. Okay, so on inside surroundings that bubble, there will be no material inside that bubble. Okay, so whenever you are going to apply that casting into some applications and you are going to provide some force on that material, so what will happen, that bubble will create that resistance up to some extent. After that, that bubble is going to get break. Okay, if the threshold limit has increased for that pressure, so due to that bubble blast, what will happen, your casting is going to get distorted. Okay, and that can create major problems. So for detecting those defects inside the casting, you have to go with ultrasonication testings or eddy current, or sometimes radiography testing. It's like X-ray. Okay, so with the help of X-ray, you can detect the you can detect the defects inside your castings. Okay, and if the number of defects is more, then you cannot use that casting in your application. Okay.
okay, sir.
Okay, anything else?
No, sir.
Okay, so good luck for your examinations. I don't know the exact date when it will happen. Okay, so I think
Yes.
this will be the this is going to be the last lecture. Maybe we will see if we can have one more class. I don't know, for your whole review of the this lecture. Okay, whatever the lectures we have taken, so we can take one review class. We will see about it if we can take it or not. Okay, so otherwise, this is going to be the last class. Okay,
Okay, sir.
okay, good luck for your exam. Okay, thank you.
Sir, pins holes again explain
Okay,
uh, in a small way.
what you are asking? You are asking some
Sir,
question, or
sir, I'm asking casting defects.
so you want me to explain one more time?
Yes, sir.
Casting defects.
Yes, sir.
Okay, okay,
Sir,
so
in
we will
first
go
page.
with these pictures. So there is one defect, microporosity. Okay, so microporosity will come due to the inclusion of air bubbles inside your casting, or inclusion of some slag materials inside your castings. So okay, so that microporosity can create huge problems whenever you are going with some pressure applications. Okay, you are going to apply huge pressures on your casting, so those micro porosity is going to create a huge problem, because during that pressure applications you will not be able to use that material, because that will not help you with the strength. Okay, then coming to the next one, uh, So these gas defects are generally blowholes or open blows, air inclusion that can come due to the inclusion of air inside your casting, entrapment of air inside casting. Then pinhole porosity is there. So pinhole porosity will be on the surface of the castings. Okay. So when we talk about pinhole porosity, that is created due to the expulsion of gases during the casting processes. Okay, when your casting is going to get solidify, okay, so whatever the gases uh, is inside the your molten metal, that is going to get out from the surface. Okay, so that will create that pinhole porosity. Okay, so why this pinhole porosity is detrimental? Because due to that pinhole porosity, what will happen whenever you are going to apply some pressure, or you are going to apply it in uh, fatigue type of applications. So what will happen on those pinhole points? Your defects will start to grow. Your crack propagation will be there. Okay, and after some time, your casting is going to get broken down in two pieces or maybe in more pieces according to your crack propagation and other things. Then coming to shrinkage cavities, these types of cavities comes during the solidification shrinkage process. Okay, when we talk about casting solidification, we talk about two different things. First is liquid shrinkage. Okay, that liquid shrinkage can be avoided with the help of risers. Okay, but because what the risers are doing, liquid is getting shrinkage, and in the riser we have provided extra molten metals. Okay, so that extra molten metal is going to fill inside that liquid shrinkage cavity. Okay, so you will not get any liquid shrinkage cavity if we are using riser inside the casting system. But to avoid solidification shrinkage. Okay, if some solidification shrinkage occurs there, then we cannot go with the riser because the material has already been solidified. Okay, so due to that solidification shrinkage, the shrinkage cavities will occur. So due to this solidification shrinkage, what will happen? It can distort the size of your final size of your castings. Okay, so to avoid that shrinkage cavities, you need to create your mold design like that it should not affect your final castings. Okay, if shrinkage cavity defects are there, so it should not create hamper your final dimensions of the castings. Then coming to molding material defects, cuts and washes, metal penetrations, fusion, runout, rat tails, and buckles or swell drop. These type of defects comes due to, if we talk about permanent mold, okay, and we are talking about two halves of that permanent mold. Okay, so we are going to join those two halves with the help of some clamps. Okay, so if the clamping is not proper, okay, so what will happen when we are going to put your molten metal inside that mold? So that will exert some pressure on the mold, and what will happen due to improper clamping of that mold? Okay, that material will going to flow out from that joint position. Okay, that will also create the, okay, that will create the run out defect. As you can see, there is run out defect, so that will create that run out defect or cuts and washes defect. Then we talk about metal penetration defect. So metal penetration defect will come due to the penetration of metal inside your sand mold. Okay, due to the high pressure, because when we are pouring the molten metal inside your castings, so that is going with very high velocity. Okay, so due to that high velocity, what will happen? That is going to uh, erode your sand. Okay, so the erosion of sand will create that metal penetration defect. Then coming to rat tails, that is coming due to similar things, and buckle swell drop, that comes due to the improper permeability of your sand mold or improper ramming of the sand mold, because that during the molten metal pouring inside your casting system, that will create the that will exert the pressure on your mold. Okay, either it is going to shrink or either it is going to expand. If it is going to expand during solidification, so what will happen? It is going to exert some pressure on your sand, and if you had not rammed the your sand properly, okay, so that will swell up. So due to that swelling up, what will happen? The final dimensions of your casting is going to get changed. Then coming to pouring metal defects. Yes. Pouring metal defects, we talk about misruns, cold such and slag inclusion. So misrun will look like this. Okay, your molten metal has not flown to the last point of your castings. It has gotten solidified before the last point of the casting. So that defect is known as misrun. Then coming to the cold suds. So cold suds is basically we had talked about, if we talk about this, okay. So we are pouring the molten metal from both ends, from this end and from this end. Okay. We have one more sprue here and we are going to pour the molten metal from two ends. Okay. So what will happen? Material will come from this side and material will also come from this side. And if this is going to get solidified before the proper fusion of the molten metal, okay, so that will create the cold sud. Okay, so in the middle of your casting, you are not going to get any metal. Okay, because that has gotten solidified before the fusion of those two streams. So that will create the cold sud effect. So that can be avoided with the help of by providing more superheat to the system, so that it can provide the more fluidity to the molten metals. Okay, so before the fusion is going to happen, it is not going to get solidified. Okay, then coming to the slag inclusion, that will come due to the during your smelting processes only. If you are not providing any filter in the filter during the molten metal pouring, so what will happen with your molten metal? The slag will also come inside the system, and if it is going to get included into your casting, what will happen? It is going to create brittleness inside your castings. Okay, because slag are generally having ceramic properties, so ceramics are very brittle in nature, so that is going to create the uh, defects inside your casting. Then coming to the hot tear and hot spots. So hot tear defects is generally uh, occur due to the improper heat transfers during solidification shrinkage. Okay, so if improper heat transfer is not there, so the hot tear effect defect will come. So for the wherever there is a corner, sharp corners, so to avoid this defect, what we generally do, we do not create sharp corners inside our castings. Okay, we what we will do, we will, if the corner you can see the sharp corner is not here in the mold, we have somehow tapered it, it's some up to some extent, so that will help to avoid that hot tear effect, because the contraction will not be there. Okay, so that will avoid the hot tear defect. So these are the different types of defect which comes during your casting processes. And to check these defects inside the casting, we have different diagnosis processes like NDT testings. So we can check those defects inside the castings. Okay.
Okay, thank you, sir.
Okay. So any more doubt?
No, sir.
Okay. Okay. Thank you guys. If any doubt is there from other two ones, you can ask. Otherwise, we will close this session. Okay. Thank you. Thank you guys for joining. Okay. We are going to end this session.